Hi. Can everyone hear me? आवाज सबको क्लियर आ रही है? एक बार चैट पे आप यस लिख दो. यस यस ठीक है. ओके ओके ठीक है, तो स्टार्ट करते हैं. तो बिफोर मतलब बिग वेबिनार स्टार्ट करने से पहले एक बार डिस्कस कर लेते हैं कि क्या क्या कवर होगा. तो सबसे पहले तो हम थोड़ा एक ब्रीफ ओवरव्यू लेंगे कि नंबर्स कैसे मेमोरी में स्टोर होते हैं, राइट? क्योंकि अगर हमें वो नहीं पता होगा तो हम आगे बिट्स मैनिपुलेशन नहीं कर पाएंगे. उसके बाद जैसे ही वो ओवरव्यू लेंगे उसके बाद सेकंड चीज हम देखेंगे कि व्हाट बिट्स आर, बिट्स क्या होते हैं और बिट मैनिपुलेशन में मैनिपुलेशन का क्या मीनिंग है. उसके बाद फिर हम कुछ कॉमन बिट ऑपरेटर्स देखेंगे जिसके थ्रू हम बिट्स को मैनिपुलेट करते हैं. और फिर उसके बाद जब सारे डिस्कस कर लेंगे फिर एक बिट मैनिपुलेशन टूलकिट हम डिस्कस करेंगे. दिस इज बेसिकली मतलब टूलकिट्स आर मतलब इनको एल्गोरिदम्स नहीं कहेंगे, इनको मैं एल्गोरिदम्स नहीं कहूँगा क्योंकि क्या काफ़ी छोटी हैं. पर ये कुछ ऐसी चीज़ें हैं जो आप सबको बेसिकली पता होनी चाहिए ताकि आप क्वेश्चंस जो मोर कॉम्प्लेक्स क्वेश्चंस हैं उनको आप अटेम्प्ट कर सको. तो कुछ बेसिक पॉइंटर्स हम इस पे देखेंगे. उसके बाद जो भी हमने बिट मैनिपुलेशन टूलकिट में जो जो भी सीखा है उसको हम क्वेश्चंस में अप्लाई करेंगे, ठीक है? और फिर फाइनली नेक्स्ट स्टेप्स में हम देखेंगे कि हम कैसे इंटरव्यूज के लिए प्रिपेयर कर सकते हैं बिट मैनिपुलेशन टॉपिक को, कैसे हम खुद इम्प्रूव कर सकते हैं इस टॉपिक पे, राइट? और क्या क्या रिसोर्सेज हैं जो मुझे यूजफुल लगती हैं जब मैं बिट मैनिपुलेशन पढ़ता हूँ. तो पहले टॉपिक से स्टार्ट करते हैं. तो सबसे पहले देखते हैं कि नंबर स्टोर कैसे होते हैं मेमोरी में. हम जब नंबर्स की बात करते हैं हम यूजुअली 4 या 5, जब भी हम नंबर्स बात करते हैं उसको डेसिमल सिस्टम में लिखते हैं. लेकिन जब कंप्यूटर्स उसको अपनी मेमोरी में स्टोर करते हैं तो वो इन नंबर्स को बाइनरी में स्टोर करते हैं. फॉर एग्जांपल जैसे 4 का बाइनरी कोड है 1,000, राइट? 5 का है 1,001. ओह सॉरी सॉरी सॉरी, दिस इज 1,000 4 का और 5 का इज 1,001. तो अब सबसे पहले प्रॉब्लम ये आती है कि कंप्यूटर्स में सिर्फ पॉजिटिव नंबर्स नहीं नेगेटिव नंबर्स भी स्टोर करने होते हैं. तो अगर हम अपने डेसिमल सिस्टम में बात करें तो अगर -4 लिखना है तो हम एक माइनस का साइन आगे लगा देते हैं जिससे हमें पता चल जाता है कि हाँ ये इस नंबर का मैग्नीट्यूड 4 है और इस नंबर का जो साइन है दैट इज नेगेटिव नेगेटिव साइन है. पर बाइनरी सिस्टम में हम नेगेटिव नंबर्स को कैसे रिप्रेजेंट कर सकते हैं? तो सबसे पहले जो लोगों ने सोचा इसके बारे में उन्होंने एक सिमिलर सिस्टम एम्प्लॉय करने की कोशिश करी कि जिस तरह हम अपने डेसिमल सिस्टम में नेगेटिव साइन का यूज करते हैं उसी तरह हम बाइनरी में भी जो मोस्ट सिग्निफिकेंट बिट होती है जैसे कि ये, उसको अगर हम साइन रिप्रेजेंट करने के लिए यूज कर लें और बाकी की जो रिमेनिंग बिट्स हैं उनको मैग्नीट्यूड बताने के लिए यूज कर लें तो हमारा काम शायद बन जाए. तो देख लेते हैं कैसे हुआ. जैसे 4 बिट्स का नंबर हम एग्जांपल लेते हैं. एक मिनट, ओ स्क्रीन विजिबल नहीं है. एक मिनट, सॉरी सॉरी, एक मिनट. अब विजिबल है क्या स्क्रीन? ओके, ठीक है, अब इंग्लिश में कर लेते हैं, दैट्स नॉट अ प्रॉब्लम. Is my screen visible? Okay, okay. Okay, we will start from the beginning. We start from the top. Let me just remove the slides. Okay. So the first thing we are going to learn is how numbers are stored in memory, right? Generally, when we write numbers, we write it in the decimal system, but computers use a different system called the binary system, which is consisting of zeros and ones. Then the second thing we are going to learn is what are bits and what is manipulation. And the third thing we are going to see is what are bit operators, basic bit operators that are used for bit manipulation. Then there's a small thing called a bit manipulation toolkit, which consists of several operations that you must know, that you must understand, which are then used to solve more complex problems in bit manipulation. So there are going to be 5 or 6 bit expressions that you will be learning. And after that, we are going to look at some questions in bit manipulation in which the things that you learn in the toolkit will be used. And finally, we will see the next steps where I will share some tips on how to prepare this topic for interviews, how to get better at this topic, and share some resources that I find useful for learning bit manipulation. Okay, so let's begin with the first topic, which is how numbers are stored in memory. Okay, so generally when we are writing numbers or discussing numbers, we use the decimal system. For example, if I want to quantify 4, I'm going to write it as 4. Right? If say I want to write 5, I'm going to write it as 5. But in computers, we use a different system called the binary system. So in that system, 4 is represented as 100, and for example, 5 is represented as 101. Now, there was a small issue in this in representing binary numbers, that numbers can't only be positive, right? They can be negative as well. But unlike the decimal system, like the system that we use, there's a simple fix for this. We can just append a negative sign to our numbers to make it to represent that this is a negative number. So if we are writing it like this, -5, the negative sign represents the sign, and the 5 represents the magnitude of the number. So when we brought this problem to the binary system, the first solution that we thought of was very similar to this, that we could use one place for telling the sign of the number and the rest of the places to represent the magnitude of the number. So for example, if there are 4 places, there are 4 digits that we can use, 1 2 3 4, and we want to represent -4. So we can write it as 100, and this represents the magnitude, and this bit at the starting represents the sign. Now it was decided that 0 would be used for representing positive numbers and 1 would be used for representing negative numbers. So 1100 would represent -4 and 0100 would represent +4. But now there was a issue with this system, and I'll tell you that. The first issue is that 0 could be represented as 1,000,000 or 4 times 0. Now, both of these numbers represent the same thing, right? This is -0, and this would be +0 according to the system. And -0 is not a thing. Both are equivalent, and both are just termed as 0. But this was not a huge problem. That's fine. Like we could, if there's one number repeating, that's not a very big problem. The major problem with the system was that when it came to adding or subtracting or performing basic operations on binary numbers, this system was not very good. For example, let's take the case of +4 and -4. And now suppose I want to add these two numbers. So what I could do was, for +4, I'm going to write 0100, and for -4, I'm going to write 1100. Now let's add these together. So 0 plus 0 would be 0. 0 plus 0 again 0. And 1 plus 1 is 2, but in binary 2 is represented as 1 0. So 1 is carried and 0 is written here. And 1 plus 1 is again 1 plus 1 is again 0. 1 plus 1 is again 2. So it's written as 1 1 0 triple 0. Uh, is there a doubt till this point? Anyone has a doubt till this point? Okay, so Dolly says no, Preeti says no, no doubt, no sir. Okay, Ayushi, which part did you not understand? Uh, okay, I'll explain binary addition to you. Some people have a doubt on that. So let's say I want to add two binary numbers, 1010 and 1100, right? So zero, now you have to first know that this number is a binary number, right? This is not a decimal number. So its addition rules are going to be a little bit different, but similar to what we use in the decimal system. So 0 plus 0 is going to be 0. We know that. 1 plus 0 is going to be 1. Uh, and 0 plus 1 is again going to be 1. And 1 plus 1. See, 1 plus 1 in decimal system is 2. But 2 is represented as 1 0 in binary, right? So instead of writing 2 here, I'm going to write 1 and 0. Now, if this 1 1 was, let's say there were some more digits after this. Let's say I want to add these two numbers. Then 1 plus 1 is 1 0. I'll carry the 1 like I do in the decimal system, and I'll write the 0 here, right? So 1 plus 0 plus 0 is 1. 1 plus 1 is again 2, which is 1 0 in binary. So 1 0, 1 is carried. And then 1 plus 1 is again 1 0. So the final answer would be 1 0 0 1 0. And since we are working with only 4 bits, so we are going to take these bits and discard the fifth bit. Now is binary addition clear to everyone? Yeah. So Itismita has said correctly. The answer is 10110. Yeah, Dolly, the video will be available later on YouTube. Okay. So I hope everybody understands addition now. See, we are discussing these bits first in a little bit detail because it's going to be very important when we learn the bit operators. Okay. So this system was not working because, like I said, the number 0 was represented as either 1 triple 0 or 4 times 0, which was both representing zeros. 1 triple 0 was representing negative 0 and 4 zeros was representing plus 0. So to represent negative numbers, a different system was being worked up, which is called the 2's complement system. Now in that system, negative numbers are stored as 2 complements of its positive counterpart. For example, again, let's take the example of 4. And if I want to store negative 4 in binary, what I'm going to do is find the 2's complement. Now to find the 2's complement of any binary number, we first take the 1's complement and then add 1 to it. So 2's complement is going to be equal to ones complement plus 1. Now, ones complement is pretty simple to find. It's just the not of a number. It's just the same number, but with all of its digits reversed. By reverse, I mean if the digit is 1, it is converted to a 0. And if the digit is 0, it is converted to a 1. So 100 is written as 011. So this would be the ones complement of 4. Now, to find the twos complement, we are simply going to add 1 to this. So adding 1 to this, we get. Does anybody have any doubt in finding the ones complement? Uh, okay, nobody is replying, so I am assuming that there is no doubt. Let me just explain again, just in case. So positive 4 can be written as 100, and we can also consider the sign bit, the one which is used to represent the sign. Now to find the twos complement of this number, first we are going to find the ones complement, which is just the same bits but reversed. So ones complement of plus 4 would be 1011. And to find the twos complement, we just add 1 to this. We just add 1 to this to get 1100. So twos complement of positive 4 is 1100. And this is the number which is used to represent negative 4 in our binary system. So this number is actually representing negative 4. Now, as you can see, every negative number starts with a 1, right? If the first bit of a number is 1, we can safely say that that number is negative. And to find the magnitude of that number, we can just reverse this process, find the twos complement of this number again, and whatever number we get, we'll get this number back. And from this, we can say that the sign is negative from this one, and the magnitude is 0100, which is 4. So we can know that 1100 represents negative 4. Okay, so now that we have that out of the way, let's move on to what are bits and what is manipulation. Well, we have already learned what bits are. Bits are nothing but these digits that we use to represent binary numbers. And the number of bits used to represent a binary number can be different. It changes according to the data type that we have. For example, an integer an integer uses 32 bits to store itself. A long uses 64 bits. So depending on the data type, the number of bits to represent the same number can change. So for this webinar, right now we are just assuming that every number consists of 4 bits, but in reality, the data type determines the number of bits used. And manipulation is when you have to, change or transform these bits in some way to reach a required output. Now, how exactly you change these numbers, or what would the desired output be, that depends on the situation and that depends on the question. But we are going to look at some bit operators that are used for this task, that are used for manipulating bits. So the first bitwise operator that we are going to look at is called the bitwise AND operator. Right? And how this works is, the bitwise AND operator works is, if you have two inputs, let's say A and B, and we are just making a table. So A and B can either be 0 or a 1, right? Just like A and B. A and B, the result of A bitwise and B can also be 0 or 1. Now it is 1 if and only if both A and B are 1. Otherwise, it's a 0. So for example, if A is 0 and B is 0, A and B would be 0 as well. Similarly, if A is 0 and B is 1, there's one 0 in here. So A and B would be 0. Again, for this next case, A and B would be 0. Now this, since both A and B are 1, A bitwise and B operators is going to evaluate to 1. Now, there are some properties that properties of bitwise AND that you should notice from this truth table. It's that whenever you take a number and AND it with 0, you get a 0, right? Regardless of what A is, if I AND it with 0, I'm going to get a 0, right? And if I AND a number with 1, I'm going to get that number itself, right? Is there a doubt in bitwise AND? Please write it, mention it in the chats. Okay, no doubt. Okay, so the next bitwise operator is going to be a bitwise OR. Now, OR is a little bit different than AND, and it's represented by this pip symbol. Now, it's exactly the opposite of AND. It says that A or B is going to be a 0 if both A and B are 0. Otherwise, it's going to be a 1. So it's like a reverse AND. It's going to be a 0 if both A and B are 0. Otherwise, it's going to be a 1. So let's make the truth table out of this. 0 or 0 is going to be 0 because both of them are 0. Otherwise, the rest of them are going to be just 1. Ashish Pal is asking how A and 1 is A. See, Ashish, A and 1 is A because let's say A is 0. Let's consider both the cases. A and 1, let A be 0. So 0 and 1 we know is 0, right? Which is equal to A. And when A is equal to 1, 1 and 1 is going to be 1, which is again equal to the value of A. So we can generalize this and say that A and 1 is equal to A. Yeah. Okay, so bitwise OR. And again, looking at the truth table, we can say that A or 1 is going to be a 1 always, right? It does regardless of what A is. And A or 0 is going to give me the value of A, right? Now let's look at the next one, which is a little different than the two that we saw. It's called the bitwise exclusive or also called XOR for short. Now it says that A XOR B is going to be 1 if A and B are different, right? Otherwise, it's going to be a 0. So A XOR B, since A and B are both same, they're both 0. So A XOR B is going to be 0. Now, if A is 0, B is 1, they're both different. So the answer would be 1. Again, in the next case, both of them are different. So the answer would be 1. And in the last case, both of them are 1, they're same. So A or B would be 0. Now, let's discuss some properties that XOR has. The first property is A XOR A is 0, which is evident from this truth table. Then, if I take a number and XOR it with 1, it's going to give me the reverse of A. which is represented as not A. Let me just write it down. Okay. Pushkar, we will come to the major part. There are other students as well. And this is we are starting from the basics because there are no prerequisites for this webinar. Okay. So the last property is that if you take A XOR 0, it's going to give you back A, right? So XOR has these three main properties. And so I hope that is clear to everyone. If there's a doubt, please leave it in the chat. Now let's discuss the final basic operator, which is the bitwise NOT. Now this one is very simple. If you take a NOT of a bit, it's going to flip that bit. If it's a 0, it's going to be a 1, and if it's a 1, it's going to turn to a 0. So the truth table for that is pretty simple, and there are no properties as such. Now there are two other properties that we should look at, which is the left shift operator and left shift operator and the right shift operator. So first, let's discuss what the left shift operator is and what it does. Suppose I have a binary number. Let's say the number is this, and I apply a left shift operator to this. What exactly it's going to do? First of all, left shift operator requires two operands: the number that is to be left shifted and the number of places that you want to left shift that number. So for example, if it's going to be something like the number itself, then the operator, and then let's say I write 2. 2 represents the position by which I have to shift this number. Now what it does is it takes this entire number and it shifts it towards the left. And what this does is it discards the first 2 bits, right, from the beginning, and it adds 2 bits to the right. So the number is going to be transformed, and it's going to transform like this. So this number, when you left shift it by 2, it's going to transform to this, right? And similarly for the right shift operator, it does a pretty similar thing as the left shift operator. It takes the left 2 bits and discards them, and it adds 2 bits to the right. Now, the right shift operator is a little special because the bits that you are adding doesn't necessarily have to be zeros, right? It can be 1 or a 0, but that is dependent on the language that you're using, and that also depends on the compiler that the language is using. But usually it is assumed that when we right shift, it's going to be the bits that are being added are zeros. There might be another assumption that that could be mentioned with the question that the most significant bit is added as when you apply a right shift operator, but that depends. If nothing has been written, you can assume that zeros are going to be put in the place. And this is only the case with right shift operator. Left shift operator, it's always going to be zeros, right? So any doubts in that, any of the operators? Will shift operators work same with negative numbers also? Yes. Yes, they will work the same. If I have a negative number and I left shift it and I left shift it by 2, then you can see that this number, 2 bits will be discarded and 2 zeros will be added. So earlier this was a negative number and it changes into a 0. Is it necessary to move 2 places? No, no, Nikhil. That number of places that it shifts is given by this number. If I change it to, let's say, 3 and write, let's take the same example, then these 3 bits will be discarded and 3 bits will be added. It depends on what number you write here, what position you specify there. I'm using 2 as an example, but it's not going to be 2 always. It depends on the position that you give. Okay, Samriddhi says, please explain right shift again. Okay, Samriddhi, if you understood left shift, then right shift is pretty similar. Let's say I want to right shift this number by 3 positions, right? So similarly to the left shift case, this time there's one small difference. Instead of the left side, we are going to discard the right 3 bits because I'm moving them by moving them by 3 positions, and add 3 new bits to the left side of it, right? So these 3 bits would be discarded, and we add 3 zeros here. Now there are some rules that what exactly the bits will be added here are dependent on the language. Like, for example, I can give you an example. In Java, there's a triple right shift operator and there's a double right shift operator. But like in C++, there is no triple shift operator. There's only one double right shift operator. So instead, what we do is we assume that it's always going to be zeros. Or in some cases, we assume that it's always going to be the most significant bit. So for some assumptions, it's going to be 1110000, and in some assumptions, it's going to be 1100. Now, I would recommend that if you ever have a question like this in an interview, it's best to ask the interviewer what assumption should you take. Like, if you should consider them to be zeros, or should you consider them to be the most significant bit, or whether if you are working with Java, then you can straight away use the triple right shift operator. Okay, we need to add 0 always at the end in left shift. Yes, Ayushi, we always add 0 at the end in left shift. Yes, but for left shift, the bits added are always 0. They're always 0, no exceptions, no dependencies on the language and compiler. Okay. Now we have gotten the operators out of the way. Now let's see how we can use these operators to manipulate bits and get some desired outputs. And now we come to the bit manipulation toolkit. And first we'll see some basic operations, 4 basic operations. The first one is set the ith bit. The second one is unset the ith bit. Third one is toggle the ith bit. And fourth one is going to be identify the ith bit. Okay. Now setting a bit means converting that bit to a 1. If the bit is already 0, we convert it to a 1. If it's already 1, then we don't change it at all. Unsetting similarly is setting, replacing a bit by 0. If it's 1, we change it to a 0. If it's 0, we leave it unchanged. Toggling is also called flipping. In that, if the ith bit is 1, we convert that to a 0. And if it's 0, we convert that to a 1. Okay. And identifying the ith bit is, if I give you the bit number, like this is the bit that you need to identify, and you just need to say whether it's a 0 or a 1, right? So, okay, so let's see that. First, let's see the setting the ith bit. Set ith bit. Now, let's say I have a binary number like this, and I is counted. Now, one special thing about I is that I is going to be counted from 0. It's a 0 counting, 0 based counting, and it's going to be counted from right to left rather than from left to right, like we usually do when we index arrays. Bits are indexed from right to left. Okay. So if I want to set ith bit and I say set the third bit for me, then the third bit is going to be this one, 0th bit, first, second, third. This is the bit that we want to set. Actually, let's take the 4th bit because this one is already set. So let's take the 4th bit. In that case, 4 would be this number. Now, the properties that we saw in the truth tables that we discussed earlier are going to be very useful for this task. Now, let's see what I really mean when I say setting an int bit. What I mean, the output that I want is for all of the other positions except 4, I want the same digits that appear here to appear in the output as well. So these would be copied like exactly the way they were. And this 0, only this bit would be converted to a 1. So this would be the input and this would be the output, right? So let's discuss that, how we can achieve that. And we wanted to convert this bit. So one property that we saw, it was related to OR, that A or 1 gives you a 1, regardless of what A is. And you notice that it is very similar to the output that we want. We want to convert this 0 to a 1, right? So what I can do is, if I can make a number here, which is something like this, 1, and then I have to decide what these other bits are going to be. And then I OR these, bitwise OR these two numbers, then I'm going to get the input that I wanted. Now, the second property of an OR was that if you OR a number with 0, it's going to give you that number itself, right? These are the two properties of OR. So we can also use this property because these are the same bits that we want in the output as well. So if we take a number that has 0 in all these places, but a 1 in the 4th place, we can get the desired output by ORing these two numbers. So how can we get this? How can we construct this number? Can anyone think of a way using the concepts that we have learned so far, using the bit operators that we have learned so far? Can anyone suggest a solution for this? Okay, some people are replying the correct solution. Samriddhi not understanding this one. Can you clear it once again? Sure, Samriddhi. What exactly did you not understand? The left shift operator, or how did we get to this number? Yeah, everybody else is correct that we will be using a left shift operator to get this number. Okay, so I'll just explain how it is. So people are commenting 1 left shift 4, right? But how exactly do we get this number? First, now 1 is stored as 1, then preceded by zeros. How many zeros? That depends on what the data type of this number is. Let's say it's int, so it's going to be preceded by 31 zeros and a 1 and a single 1 at the end, at the 0th position. Now I want to bring this 1 here to the 4th position, and then I'll get this number, the same number that I wanted. Now the left shift operator is going to help me because what it does is, as we discussed, it's going to discard the first 4 bits, right? These are going to be discarded, and it's going to add 4 bits at the end, right? And left shift operator always, adds a 0. It always adds a 0. There's no chance of one being added. So by doing 1 left shift 4, we can form this number, right? So after getting that number, and so this number is 1 left shift 4, and to generalize it for I, we can write it as 1 left shift I, right? And if the given input was represented as X, then I can do a bitwise OR of X and this number to get the desired output. Can't we put the required number directly? Yeah, we are putting the required number directly, Isha. And yes, also Nathan, then we won't lose the point of learning bitwise. And see, you can do this question even without bit operators. Like, because one left shift I, if you notice, it's nothing but 2 raised to the power I. Why? Because let's say I is equal to 4, and then I have 1 followed by zeros. And this is. So now in the binary system, as you know, this is the 0th position, first, second, third, fourth. This digit is represented as 2 raised to the power 0. This is as 2 raised to the power 1, 2 raised to the power 2, 2 raised to the power 3, and this is 2 raised to the power 4. Similarly, like in the decimal system. So all of these are zeros, so we will not count these numbers. But this is a 1, so we'll count this. So it's going to be 2 raised to the power 4 in our decimal system. So one left shift I actually gives you 2 raised to the power I. So instead of doing this, we could have also written, we could have used a power function 2 comma I. But this function is slower than using bit operators. Bit operators are really fast. That's one of the advantages of using bit operators. Okay, so we got this answer by we make this number, and this number is usually commonly called a mask. It's called a mask. It's called a mask because you are combining it with some other number. You're covering that number with some other number to get a output. So that's why it's called a mask, because it covers the entire input. Okay. How 2 power? 2 power because it's a binary system. Binary, because it's a binary system, so we are doing 2 raised to the power 4. Because every one of these digits represents a power of 2. That's why it's called a binary system, because they are storing powers of 2, and 2 is binary. Hitesh, so in general, x left shift k is equal to x into 2 raised to the power I. No, 2 raised to the power k. Yeah, instead of I, it's going to be k. But yes, you are correct. X left shift k is going to be x into 2 raised to the power k. How we will store the bits while coding? You don't have to store the bits. You just have to store the number. Like if you do int x equal to 54, now x is going to be stored as the binary form of 54. You don't have to code something else to tell the computer that you store it as binary. It's going to do that by itself, right? We see it as 54, but the computer sees it as the binary form of 54. So no need to store the bits while coding. That is done automatically. Can you take one more example for this? Sure. So let's say another number, and let's say we want to set this bit. So this bit is going to be 0, 1, 2, 3, 4, 5, 6, right? So the 6th bit, and then there are going to be some zeros, leading zeros, depending on the data type. Now I want to create a number. Which is exactly the same as this one, but this bit, the bit that we wanted to set, that is a 1. That should convert to a 1. If it's a 0, it should convert to 1. If it's a 1, it should convert to 1 again. And these other bits should remain the same. That is the output we want. So the way we could do that is by looking at bitwise OR's properties. A bitwise OR gives you an A, and A bitwise 1 gives you a 1. So we use these two properties to make a number, or also called a mask. And then we bitwise ORed these two numbers to get the desired output, which is going to be these many zeros: 1, 0, 0, 1, 1, 1, 0. Nitin, I won't be able to show it on Python because I don't know Python. I do know C++. I'll share the codes with you if you want, but we'll do that after the webinar. I'll share a link in the comment section after this webinar is done. Okay, so the next the next item on the toolkit is unsetting a bit. Unset the ith bit, right? Now, in this, similar to the setting of bits, unsetting a bit means converting a bit to zero. If it's a 1, you convert that to 0. If it's 0, you don't change it. So let's say again we want to unset this bit, which is going to be the 4th bit. So in this case, I equal to 4. Now, what I want, the output that I want is going to be these bits should remain the same as do these bits. So these bits will remain the same. And this bit, the 4th bit, is going to convert to a 0. And if we look at the truth tables, we can see that and bitwise and operator can help us here, because a and 0 gives you a 0 and a and 1 gives you a, right? So that is very similar to what we want. We want a 0 at one place and we want the same bits in the other locations. So we can use this somehow. So the mask for this, to achieve this, would be a 0 here and 1s in all these places, right? And if we add these two numbers, we are going to get the desired output. Now, this is a little different from the mask that we created in the last section. Instead of being a 1 here and the rest of them are zeros, this is a flip of that number. This is a flip of that mask. It's going to be a 0 instead here, and it's surrounded by 1s. So we have seen an operator that does this. So can anyone give me what exactly can be used to make this mask right here, I equal to 4? Okay, not. Yeah, so Rajat and Harish are correct. Isha Anand, yes, Isha Anand, we are going to Isha, we are going to use the ones complement, which is the same thing as doing a not. Not of a number is the same as its ones complement. So let's not tackle this problem first. Let's make this number, this upper number first. And we have already seen how to do that, right? If I left shift 1 by I, or 4 in this case, I'm going to get this number. And to get the mask that I want, I'm just going to not it. So this is the symbol for not. And now I take this mask and actually let me write it in the next sheet. So I take a not and it with my input, which is x. We are representing it as x. So I'm going to get my desired output, which is to unset the ith bit. So the general form would be I here, and we AND it with x. So is there any doubt in this? No, Chaitanya, not. This is not for 2's complement. This is for 1's complement. 2's complement is 1's complement plus 1. So you add a 1 to the 1's complement. Yes, Rahul, the video will be available for the future. Okay, no doubt. Kunal, how will we tell 4 times 1 is negative or positive? Because it can represent both. No, Kunal, in this 2's complement system, if your most significant digit is 1, it's always going to be a negative number. Provided that I'm assuming that the number system that you're using consists of 4 bits, right? If I have a 32-bit system and my 31st bit is a 1, then that number is going to be negative. Okay. Okay, no doubts. Okay. Okay, so let's move on to the third one, which is toggling the ith bit or flipping. It's also called flip. Now, flipping means reversing a bit, or reversing means if a bit is 1, you convert it to a 0, and if it's a 0, you convert that to a 1. So in this case, let's toggle this one, and this is going to be the 4th bit again. Okay, so I equal to 4 in this case. So what can we do? Like, we have seen an OR that we used, we have seen the AND operator used. Maybe the XOR operator can help us here, right? So let's look at the properties of XOR. So can you tell me what A XOR 0 does? Ruby will get to the questions that companies would ask in interviews. Sumit, bit manipulation is not different in Java. There's just one operator in Java, which is not available in C++. I don't know about Python, but it's not available in C++, which is the triple right shift operator. So you can read about that. Basically what it does, it guarantees that when you're doing a right shift operator, it appends zeros instead of the most significant bit. Okay, so A XOR 0 is, you're saying it's A itself, and A XOR 1 is going to be? A XOR 1 depends on A, okay. Yeah, so Chaitanya is correct. A XOR 1 is not of A. And not of A is basically what toggling means, right? We are calculating the not of A. If A is 1, it's 0. It becomes 0, and if it's 0, it becomes a 1. So again, we can think of a mask where this bit would be a 1, and the rest of them would be all zeros, right? And you know that A XOR 0 gives you an A, so all these bits would remain unchanged. This bit would be toggled, and the rest of the bits would remain unchanged. So this would be the output that we get. So to toggle or flip the ith bit, and to make that mask, we have seen it multiple times. You do I left shift, one left shift I. So to toggle the ith bit, we take the input and we XOR it with this mask with I left shifted by one left shifted by I positions. Okay, so is there any doubt at till this point? No, no. Okay, so there's no doubt. So let's move on. Now the last basic bit manipulation that we'll see is identify the ith bit. Uh, Now, in this, what we want to do is, instead of converting the input to some other output, all we want to know is which bit 0 or 1 is present at the ith position. So for example, if I have a number like this, and I say let's identify this bit, whether it's a 0 or a 1, which is going to be the third bit, I is equal to 3. How can we do that? Can you think of a mask for this task? Can you identify, maybe a mask or the operator to be used that can get us to this, that can help us identify what bit this is? Nitish, I'll share the code after this webinar is over. Like I write the code, but it's going to be in C++, so fair warning. Or maybe I can even do it in Java if you want. But it's going to be after the webinar is over. Like I will post a comment on the YouTube video and you can see that. XOR of that number. So Aditya is saying XOR of that number with what, Aditya? Okay, X and you're saying that, okay, some people are saying X and one left shift I. So let's see what it does. So one left shift I is going to give me this mask. And if I AND it with X, I'm going to get zeros here. I'm going to get a 0 here. 0, 0, 0, 0. Okay, so how did this help me? And if this were a 1, what would the output would have been then? Okay. So a lot of you know this manipulation already. So let me just discuss it once. So the mask is correct. We are going to use this mask, one left shift I, and the operator is also correct. But how is this expression going to help us to identify what bit this is? So let's consider both the cases. Let's say I have a number like this, I equal to 1, this one. And let's say I have another number, which is, again, I is equal to 1, and I want to identify this number. The mask for both these numbers is going to be the same, right? Now, in the top case, if I add these two numbers, I'm going to get a 0 here, a 0 here, and 0 here. Like, because my mask has all zeros, all of these bits are going to be zeros, except this one. For this one, it depends, right? It depends on what this bit is. If this bit is 1, my output is going to be 0, 0, 1, 0. But if it's a 0, like in this case, it's going to be all zeros. So, and see, you know that if there is a 1 in a binary number anywhere, if there's a 1 present in a binary number anywhere, like in any position, we know that that number is non-zero. Not necessarily positive, as people are saying, although they are correct in this case, but it's going to be non-zero, right? Because if there's a 1 at the 31st position and it's an integer, then it's not going to be greater than 0. It's going to be not equal to 0. So this is the condition that we should ideally use. This is more safer than this one. And if the ith bit were a 0, then the entire number would have been 0, right? So how we can identify this number is, I do an X and with the mask, and if this expression evaluates to a 0, then I know that my bit was unset. The ith bit was unset. But if this expression was anything but a 0, negative, positive, doesn't matter. If it was anything then a 0 other than a 0, then it's going to be set. So do you have any doubts till now? Okay, Rajat is saying no doubt. Anyone else? Nitin is saying, can you please repeat? Which part do you want me to repeat, Nitin? The purpose of identify, we'll get to that. We'll get to the purpose of identifying. Vaishnavi is saying, what is mask? Vaishnavi, mask basically means this number that we construct, right? Like I don't know the origin of why it's called a mask exactly, but the number that we construct and then we apply a operator with the original number to get some desired output, whatever that output may be. This number is usually called a mask. Nitin, as in what is identify? Identify means we are identifying whether that bit is a 0 or a 1. We are identifying it, that ith bit is 0, or ith bit is 1. That is that is what I mean by identification. Okay. Okay, so okay, so there are no more doubts. So let's move on to the next one, right? Okay, now before I move on to the next one, there's a small question that I want you to attempt. Let's say I have, and Nitin, this is where we will use that identification. The one solution of it involves identification. So let's say I have a number like this, and there are some trailing zeros. Let's say it's a 32-bit number, 32 bits in total. These are all zeros. And I want to find out the number of set bits or the number of ones in this number. So in this example, there are these 4 ones. So my output should be 4. So, so there are 4 set bits. So my output should be 4. So how can you find this? Like if I give you any number and I want you to find the number of set bits, how can we do that using the using all the operations that we learned in the last few sections? I don't know if there's a certificate. We'll have to ask the through the proper channels. So using a dictionary, Subhadeep, how will you use a dictionary in this to find this? Count of X and so ideally we are going to, I want you to think in context of the last few sections. Like there is one, like I can tell you what it is. It's the identifying bit one that we have to use here somehow. So we want to identify each of these bits, and whenever we find a 1, we are just going to do a +1 on our count. But how would we go from, how will we check all the bits? Looping till number becomes 0 and left shifting and checking every bit. Okay, yeah, that's good. That's a possible solution. Right shift 1 at a time and with 1 for the 0th bit, yes. While X count. Okay. Okay, so you guys, okay, so all of you are presenting with correct solutions. Basically, what we want is we want to check each bit starting from the 0th bit and going till the 31st bit, assuming it's an integer. And we want to apply that identifying bit expression. Like we want to identify all of these bits. And whenever we identify a bit as 1, we are going to keep a count and increase that by 1. So since there are only 32 bits and the number made by these bits can be pretty large, we can say that the time complexity of this solution is big of 1 because there are always going to be 32 operations. But there is another solution possible, which instead of checking every bit, it jumps from the one set bit to another. And as soon as it reaches this bit, it stops the execution. So the time complexity for that solution is just going to be big O of set bits, the number of set bits. So is there a way that we could, instead of checking every bit, we just go straight to the bit that is set? Is there a way we can do that? Okay, so Rajat is saying XOR. How would you use XOR here, Rajat? Okay, Harish has the right idea that A and A minus 1 gives us that. Okay, so let's discuss this. First, I want you to see I'm going to perform a basic subtraction. Let's say I have a binary number like this. Yeah, let's keep it like that. And this is, let's say, X. And I want to subtract 1 from this number. How would you do that? And what would be the result? So, see, since 0 is smaller than 1, we'll have to take a carry from somewhere. And the first digit that can give us a carry is right here. Now, this is the last set bit or the lowest set bit of this number, right? Or the rightmost set bit. Like it's called the lowest or the rightmost set bit or the last set bit. So it's going to take a carry over from here. So when it takes a carry, this will become a 0. This will first become a 2 because it takes a 0, but then it has to carry a 1, give a 1 to this 0 as well. It's going to convert to a 1. Similarly for this, it will first become a 2 and then it will become a 1 because it has to carry over 1 here as well. And this finally becomes a 2. And I'm writing 10 because it's binary for 2. So 10 minus 1 is 1 in binary. All of these ones will just be written like that. And this last 0 is going to be written as 0. And rest of the bits are going to be the same. Like there's going to be no change in them. So what X minus 1 does is it looks at the rightmost bit, set bit, and it inverts all of the bits that come after it and that bit itself. See, that's exactly what it's doing, right? It's inverting these bits, the bits that come after it, and and it inverts itself as one, itself as well. So it inverts 1 to a 0, and it inverts the rest of the bits, and it leaves the bits to the left of it unchanged. So that's what effectively x minus 1 is doing in binary system. So is that clear to everyone? Okay, Sumit is saying to repeat. Okay, I'll take another example. Let's say I have a number like this, and I want to subtract 1 from it. Now, since 0 is less than 1, so we can't subtract it with anything. So we have to look for a carry. And the first carry we find is here, which is the lowest set bit, right? So when we take a carry, this is going to convert to a 1. It's going to give a 1 here. It's going to make this into a 2. But it has to convert a 1 to the next 0 as well. So it decreases to 1. And then this bit becomes a 2. And now we do the subtraction like we did. See, this is exactly the same as we used to do in the decimal system as well. But we are doing the same subtraction in the binary system. That's the only change. So 10 minus 1 is 1. 2 minus 1 is 1. This one will be copied as it is. And then a 0. This was converted to a 0. And the rest of these numbers would be the same. So the only difference between these two numbers, x and x minus 1, is that all of the bits after the lowest set bit and the lowest set bit itself were inverted, and all of the other bits were left unchanged. So that is something that we should note. So is it clear now, Nitin and Sumit? Yes, the first zero, the first one, yeah. The first zero from right will be one from right. Chaitanya, could you repeat? Could you? Okay, Divya is asking what if the number is something like this? See, Divya, if the number is like this, then straight away 1 minus 1 is 0, and the rest of the bits will be copied. And again, the hypothesis that we made that all of the bits after the lowest set bit and the lowest set bit itself will be flipped, will be inverted. So that's exactly what's happened here. Since there are no bits after this one, nothing, we don't look at that part. But this bit has been inverted. See, it was a 1 and it has become a 0. And these rest of the bits remain the same. So the same thing is happening. Regardless of the position of the first one or the lowest one, this hypothesis remains true that all of the bits after the lowest bit and the bit itself are inverted. Okay, first 0 from right after subtraction will be 1 from right before. Yes, yes, Chaitanya, you're correct. The first 0 from the right side was actually the first one before the subtraction. Okay, so now that we have that, now we have a x and a x minus 1. Now, if I do an AND of these numbers, since these are all inverted, and that means there's at least a 0 present in all of these positions, either in x or x minus 1. All of these bits in x and x minus 1 are going to convert to a 0, right? And the rest of the number is going to be unchanged. It was unchanged in x because that was the original number. It was unchanged in x minus 1, and they also remain unchanged in x and x minus 1. So what this effectively did is, what x and x minus 1 did is, it converted the lowest set bit to a 0 in one operation. In one operation of x and x minus 1, or maybe you can consider it to be 2. If this is one operation, this is 1. But in order 1 complexity, basically, we have converted this, we have cleared the lowest set bit of this number in one operation. Okay, so there are no doubts, it seems. Okay, so I'll continue. So if we could, so if we can clear a bit, if we can clear a bit in one operation, if you clear this bit and the number gets converted to this, now the next lowest set bit is going to be this one, right? And now if I consider this to be our number, this to be x or n, and if I do AND of this x with again x minus 1, I'm going to clear this set bit as well, right? Yes, Chaitanya, you're correct. We have to look for a and a minus 1 till a 0. Yeah. So basically what we're doing is, let's take a number with a few more ones in it. So every time what I'm doing is, I'm going to do this x and x minus 1, and I'm going to remove a 0. And I have to do this, the number of times that I have to do this is the same number of times that that there are ones. So if there are 4 ones present, this operation can be done 4 times. And when will we know, like, how to write it in a program? How will we know that we have to stop now? Ultimately, what's going to happen is every set bit in that number, it's going to convert to a 0, right? And if every bit is a 0, then the number by itself as a whole is a 0. So while x is not equal to 0, right? It would be incorrect to write this x greater than 0 because there could be a negative number. So it's always safer to write this x not equal to 0, right? Or you could just write while x. So while x is not equal to 0, x is equal to x and x minus 1. And every time you're going to do a plus plus count, you're going to increase your count by 1. And after that, you can return that count or print that count or whatever you want to do with that. And another way to write this would be x and equal to x minus 1. Bit operators work the same way as arithmetic operators. So if you write x plus equal to 1 and it adds 1 to x and assigns it to x, same thing happens here. If you do x and equal to x minus 1, it's going to take a and of x. It's going to take a and of x with x minus 1 and assign it to x, back. So the time complexity for this piece of code, it's going to be order of set bits, count of set bits, set count, let's say. Now, see, big O, if you do this operation 32 times, or if you do this operation maybe 5 times, it may not seem like a very large difference if you're doing it just once, if you're just doing it for one number. But let's say you have to do this for a lot of numbers, and the numbers are pretty large. Let's say they are long integers. Then the difference starts to show up. So that's why this is actually a very useful optimization to find the count of set counts, set bits, count of set bits. Okay. Samriddhi is saying if number is like 100101, then the lowest set bit will be the rightmost one. Yes, Samriddhi. The lowest set bit will be the rightmost one. By lowest, we mean the rightmost one. And it's called lowest because, see, the reason it's called lowest, because this one, the value that this one is contributing to the number is the lowest out of all the other ones. For example, if this is, as you know that this position is represented by powers of 2, all these positions. This 2 raised to the power 3. This is 4, 5, 6, 7. This would be 2 raised to the power 7, 8, 9, 10. This would be 2 raised to the power 10. So this contributes the lowest amount out of all of these ones. That's why it's called the lowest set bit. So that's where the lowest word comes from. Please explain the alternate code. See, Apul, if I write x equal to x plus 1, what does it do? It calculates, it adds 1 to x's value, and then it assigns it to x, right? And there's a way you write it in C++ and Java, at least. I don't know about Python. Another way you can write this code is x plus equal to 1. Now, this code does the same thing as this. So what I'm saying is that bit operators are similar to arithmetic operators in this regard, in that they can also be written like this. That if you want to do x equal to x and x minus 1, you can make the code shorter and straight away write x and equal to x minus 1. That's it. Yeah, shorthand operator. It's called a shorthand operator. Okay, can you explain the loop code again? Sure. See, okay, let me just do a dry run on the example that Samriddhi gave, so that Samriddhi and Sumit, both of you will understand. So let's say x is this, right? Now I do while x is not equal to 0. This is important. I have to do some operations. Now the operation that I'm going to do is x and equal to x minus 1. What it's going to do is assign x the value of x and x minus 1. Now in the first iteration, what's going to happen is 100101, and I do x minus 1, it's going to be 100100, and I add these two numbers, I'm going to get this number, right? So in the first iteration, x is transformed to this number. It started from this and we came to this, right? And in every iteration, we are also keeping a count of how many times the loop has run, right? Now in the next iteration, again we do x minus 1, and in this case x minus 1 is going to be this, Again, we do an and we get this. So we removed another set bit. And now X has transformed to this number, 1, then 5 times 0. And again, we do a plus plus count, right? So we have counted 2 bits so far. So count is equal to 2 currently. And the final time, this most significant one, because every other bit is 0, every bit to the left of it is 0. So this would be the last set bit. Again, I do X minus 1 and AND it with X. So this time I get a number like this by doing X minus 1. This is X minus 1. And I do AND of this, so I get all of them as zeros. And count is increased by 1 again. And finally, X is now 0. And this while loop was running while X is not equal to 0. So the condition now breaks. It is false. So the while loop is broken. And now we get the count as equal to 3. So that means there were 3 set bits in that original number that we had, which was this one. And you can see that this that indeed that it is 3, that there are 3 set bits. Okay. Rajat is asking why it can't be X greater than 0. Because see, maybe it could be that I give you a negative number and then I tell you to count bits of that number, right? And like I said, negative numbers are also in negative numbers, the most significant bit is 1. So you can have a number like this, maybe triple ones, and then there are 29 bits which are just zeros, right? So a number like this would be positive. That's why we can't do while X greater than 0. We have to do while X is not equal to 0. Okay. Okay, so Ashima got it, and Rajat, did you get it? Okay, got it. Okay. Now let's say instead of clearing the lowest set bit, I just want to make a mask that looks like this, right? Now, this is different from the examples that we have seen before, because in those examples, we knew the value of I, right? So we could straight away do 1 left shift I and get this mask. Let's say I don't know the value of I, but I want a mask that that has a 1 in the lowest set bit position and a 0 everywhere else. So how can I do that? How can we do that? So the basic, the brute force solution would be to again identify every bit, and the first bit that we get as I, we can have a count which could tell us that okay, the third bit was a 1. So we break the loop and do I left shift 3, and we get the mask. But again, we want this to be a big O of one operation, one as in one operation only. We want to find the mask. So how can we do that? By using only X. We don't have any other values. And Rashi, it's not yx not greater than 0. It's yx not equal to 0. Maybe I wrote it like this by mistake. It's not equal to. This was an equal to sign. Okay. Okay. It seems like some people are still have a problem with the x greater than 0 thing. I'll just explain it to you again. Let's consider all of the 32 bits, right? Let's say I have an integer, and the integer is 1 0 0 1 0 0 1, and then rest of them are all zeros. And these all are 32 bits in total. Now, as we discussed in the very first section when we were discussing that negative numbers are stored as 2's complements, we saw that every negative number, the most significant bit of every negative number is 1, right? That's how the computer, or that's how even we identify that this number, whatever it is a negative number. Like I'll have to calculate the magnitude. It's going to be 2 to the power 31 and all that. But one thing that I can say just by looking at the number is that this is going to be a negative number, because the most significant bit is 1. And if I give you this same number and I ask you to find the number of set bits, I can't do while x greater than 0, because x is not greater than 0. Because in this case, in this particular case, x is negative. So x is less than 0. So your while loop won't be executed even once, and the value of count that you will get is 0, which is obviously incorrect. That's why it's very unsafe to use x greater than 0 in bit manipulation questions. It's much better and safer to use x not equal to 0 instead. Okay. Okay, so now everyone is clear with this part. Okay, got it. Now it's clear. Okay. Okay, so let's go back to the question that we were discussing before. The question is, if I want, this is a number, and I want a mask that, actually, let me take a better number than this. Let's take a number like this, maybe. Yeah. So now I want a mask that has a 1 in the same position as the lowest set bit of the original number, of the input number, and zeros everywhere else, right? So now this problem is a little bit different, because you don't know the value of I. Like, you don't know which bit is going to be the set bit, right? So now you have to make that mask without knowing the value of I. One solution could be to sorry. One solution could be to traverse through every bit, identify them, and the first bit that you identify as 1, we can just do I is equal to that position. Let's say if the loop you are running runs 3 times, then you know I is equal to 3 or 2, sorry, and you know that the second position is the one that you want to make the mask of. But what we are looking for is a solution that doesn't do this in 32 operations or number of bits operations. We want this to be a true big of 1 operation. Like, in 1 operation, I want to get this mask straight away. So how can we do that using all of the operators that we have learned so far? And see, whenever you have a problem like this, it's a very, like, what I generally do is, there are 2 things to put in here, right? This is going to be either an and or a XOR, and this number could be, see, possible, there could be any number of things that could be placed here. But the numbers that I usually try out first are n-1, n+1, and negative of n and not of n, or not of n+1, not of n-1. So the same operations like this, but with not of n instead of n. So these are the first operations that I try, and usually if the output is simple enough, I usually get it. So my advice to you would be, if you have never seen this question before, that you can try one of these. Maybe you can experiment with these 3 operators and these numbers. Yes, Aditi, the video will be available later. Samriti, the problem statement is, I want to generate a mask which has a 1 in the lowest set bit position and a 0 everywhere else. So instead of giving you an I straight away, like giving you the position straight away, I'm just saying that you have to find the position of the lowest set bit first and then make a mask for it. Okay, Aman is saying x XOR x and x-1. Is this correct? Let's see if this is correct. X and x-1 is going to clear the set bit, this bit for me, as we have seen this earlier. and you're saying to XOR it with X. So X is here. And if I XOR these two numbers, I'm going to get 0, 0, 1, 0, 0. Okay, that worked. Very well, Aman. That worked. Here except lowest bit is not changed. So what we have to do? Yeah, we are getting to that pile. Okay, Nishtha is saying we can do x minus 1 and we get first 0 at that ith position. So we know ith value. Now we can do left shift afterward. Anant is saying x and minus x as in Fenwick trees. That's also correct. And that was the one that I was looking for actually. Aman, what you said is also correct. X and x minus 1. And this is actually equivalent to this, as you'll see right now. Okay. So to get the mask, I'll just write the number again here again. Okay. So to get the mask of the lowest set bit like this, we can do this operation. And let's see first why it works. Now, negative x can be represented as not of x plus 1. Why is that? Because see, when we looked at the 2's complement at the very beginning, I told you that to convert a number to its negative form, we first take the 1's complement and we add 1 to it to get the 2's complement, right? So if I have x and I want to get negative x, I can find the 1's complement of x, which is not x, right? And then add 1 to it, which is this whole thing is going to be the 2's complement. And 2's complement is nothing but negative of x. Okay. So to get negative x, what we can do is not x plus 1. So did everyone understand till here? Okay, so Rajat is saying yes. Yes, yes, yes. Okay. Okay, so I guess there are no doubts. So let's continue. So let's take an example first and write it as, let me actually take a small example. And let's find the negative x first. But before that, let's find the not of x, which is simply going to be 0, 1, 0, 1. Then to find the 2's complement or negative of x, sorry, all we need to do is add 1 to not of x, which is going to be this. Kalyant is saying, please repeat. Okay. See, Kalyant, when we discussed 2's complement in the very first section, I told you that 2's complement is nothing but 1's complement plus 1, right? And the reason we use 2's complement is to get the negative of a number, right? Because that was the problem that we had initially with the binary system, was that to store a negative number in the computer, we were first using signed bits, but there was a problem of doubling of zeros. Zeros was being, represented by two numbers, which could have caused some confusion. So instead, we came with a 2's complement system that could store negative numbers. And to find the 2's complement, we first find the 1's complement, which is nothing but not of x, and then we add 1 to it. And we then get negative of x. So all I've done is written that as an expression, that negative of x is equal to not of x plus 1. So Kalyan, did you understand it now? Okay, yeah. Okay, so Kalyan's understood. Okay, so let's move on. See, now if we compare x with negative x, again we notice something, right? And the thing we notice that again is that the lowest set bit and every bit after it has remained unchanged, and every bit before it, before the lowest set bit, has flipped. Actually, let me take a bigger example, a longer example. Let's say I have an example like this. This is x. Not of x would be 0, 1, 1, 0, double 1, 0, 1, 0. And we add 1 to get negative x. It would be actually should have taken more zeros here. Yeah, so let's add 1. Okay, so see again, the lowest set bit and every bit after it has remained unchanged in negative x, but every bit before it has flipped, right? And that, see, you can see why that's happening is because when you flip the bits, all of the zeros that come after the lowest set bit will convert to ones, and when you add a 1, you're going to get 3 zeros. Why? Because 1 plus 1 will always give you 2, which is 1 0 in binary. So every time you're going to carry 1 to the next one in line, and you're going to get a bunch of zeros and then a 1. See, that is the reason why. And when you compare it to x, you see that they turn out to be the same. They convert back into zeros. You started with zeros, flipped them, added a 1, and it converted. They were converted back to zeros. So that's an intuitive way of looking at it. Why it exactly works, why it's working. Okay. So now we get that, we get x and we get minus x. Now if we do apply the okay. Okay, guys, can everybody hear me? There was actually an electricity problem here. Okay, 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 sure. Okay, so let's jump back. Yeah. Okay, so let's discuss the problem that we were discussing. Yeah, so we were comparing x and negative x, and we saw that every bit after the lowest set bit in x was unchanged in negative of x, but every bit before it was flipped, right? So now if I do an AND of these two numbers, these bits are going to be the same, but these bits, because they are now flipped, is going to give me all zeros. Because if they are both flipped, then at least one bit is 0. And if there's at least one bit as 0, we know that bitwise AND gives a 0. So all of these bits will be 0 and this will be a 1. So by doing x and negative of x, we get the mask for the lowest set bit. Okay, so did everybody understand that? If there's a doubt, please mention it in the chat. Anand, it's x and negative of x. And since we know that negative of x is nothing but not of x plus 1, so you can also write it like this. This not is only for the x, not for x plus 1 as a whole. After plus 1 equal to 0, but why all 0 after 1? See, Priyanshu. Yeah. So let me just take an example. Let's see. Suppose this is my number and I do a not of x first, right? And then I add 1 to it. See, before we even add 1 to it, you should notice that after the lowest set bit, every bit is going to be 0. Or if the lowest bit is the last bit, then there's going to be nothing after it. But if it's not the last bit, every bit is going to be a 0, right? Otherwise, this wouldn't be the lowest bit if there were any single one present here. And similarly, if you flip it, every digit after this lowest set bit is going to be a 1, right? And because of that, because it's going to be like a continuation of ones, if my number was something like this, right? If I flip it, my number is going to be 0, and then all of these would be ones. Like all of the zeros would be replaced by ones. And now if I add a 1 to this number, I'm going to get all zeros down. Why? Because 1 plus 1 is 2 in decimal and 2 is 1 0 in binary. So I take the 1, I carry it over here and write the 0 down. Again, I get a 1 plus 1. So again, I get a 1 0. I carry the 1 and write down the 0. And similarly, for each of these ones, I'm going to get a 0 down. And for the last, which was originally the set bit, has now been converted into 0. All I'm going to get is a 1 plus 0, which is just 1. And the rest of the bits would not be changed. So that's why I get the same thing after doing this as I had before. If I had a 1 with some zeros, again, I'm going to get 1 with all these zeros. And all of the bits before it have been toggled. See, these both are different. And so if we do an AND, I'm going to get the same 100 here, and these all are going to be all zeros because they are inverse of each other. And so by doing this x and negative x, I get a mask which has a 1 in the lowest set bit position. Okay. Okay. So any other doubts? You can mention them in the chats. Okay. Priyanshu is saying no. All clear. Okay. Got it. Okay. No. Okay. So let's continue. So see, we have covered a lot of these small bit manipulations. And I just want you to know that this is like not the end. There are a lot more. But what I'm going to do now, like not now, at the end of the webinar, I'm going to share a link which has all these bit manipulations. And what I want you to do is, instead of just memorizing them, I want you to figure them out yourself first. Like read the description of what that manipulation does, and then try to figure it out yourself. Right? That would be really great practice, because these little manipulations form the basis of all the other problems that you will be doing. Because this is just the beginning. like bit manipulation is a pretty big topic, and it's very difficult to cover it in a 2-hour webinar. But these are the ones that I find are like very common. Like there's always some question that uses these. So I decided to explain these ones first. So now let's discuss some problems, right, in increasing order of difficulty. And the first problem is actually, it is one that you might have seen before. So let's say I have an array in which, or a randomized array, there could be random numbers, there could be negative numbers as well. But one thing is, every number occurs twice, right? So let's say if there's a negative 31 here, maybe there's a negative 31 somewhere else as well, 26 maybe right here, maybe a 13, 7, 13. All of the numbers that appear in the array appear once, except one. One number, not one, the number, like one, counting one, like one number is going to be present such that it occurs only once. All the other numbers occur twice. This particular number appears only once. And we need to find out what that number is. And before you jump into the bit manipulation solution, I just want you to first suggest some solutions that don't use bit manipulation, that you could do without using bits. Yes, the video will stay on YouTube channel. Okay, yeah, we can take XOR of all elements, but like I said, maybe first let's explore some other solutions, because the XOR solution only works in very particular scenarios, that all of these repeating digits must repeat even number of times, and the number that's not repeating should be either not repeating or odd number of times. Only then you can use XOR. But let's say a very general problem, that we have some elements that are repeating and one element that is not repeating. So how can we find that not repeating element? Okay, hash map. So most of you are saying hash map, which is correct, yes. So the time complexity, let's discuss the time complexity. So what you're basically saying is, if we make a hash map, then we can get a frequency of all of these elements. Let's say frequency of negative 31 is 2. Like all of the elements, you're going to get a frequency of all of these elements as 2. And there's going to be one element, the frequency of which is going to be 1. So we can just identify them, that number, by traversing the map, and we can report that number. But and this hash map can be created in big O of n time, where n is the number of elements. But it's taking some space, right? You're using some extra space to store this hash map. So is there a solution that doesn't use extra space? It may take more time, but it shouldn't take extra space. Or it can take extra space, but that should be constant. It shouldn't depend on it. So can you think of a solution like that, where we don't use extra space? Okay, Geeta is saying sort the array, then compare with adjacent element. No 24 blank array. We can, okay, Rajat is saying we can go to index of a blank array and increase by 1 if it occurs once, and then negative ones for other. Rajat, you have to explain it in a little more detail. Okay. Okay, so yeah, everybody's saying to sort the array, which is correct. If we sort the array, the elements that are together, that are the same, will come together. Like in that case, negative 31 is going to come first, then the 7 is going to come, then the 13. Yeah, then the 13, and then the 226. So this will be my array, and then I can just traverse this array, and the number that is not repeating is going to have different elements at its left and right. And if the number is at the end, it's going to have a different number. at the left side or a different number at the right side if it's this one. So these two are the edge cases. But for all other elements, if the left side element and the right side element are different, then we can say that that element was the unique one. So the time complexity of this solution would be n times log n. See, time complexity. And the space complexity is going to be big O of 1. Assuming that we are doing a quick sort, and that quick sort takes average amount of time, because quick sort takes n square time in lowest case. So let's assume that it takes n log n time, and we don't use any extra space for quick sorting. So space complexity will be big O of 1. Now, before we move on, one thing to note in this question is that these two solutions rather is that they work even in those cases where the elements might not be repeating twice, right? They might be repeating any number of times, and the single digit will obviously be single, but the repeating elements can repeat like twice, thrice, four times, any number of times. So that these are solutions to more general problems, right? But in this question, we have given you an extra constraint or an extra help rather, that the elements that are repeating only repeat twice. So why twice? Why not three times? Or why not four times? So let's use that information first. Why and what? How exactly bit manipulation can help us if it's only repeating twice, right? So let's see. Let's take a smaller example this time. Let's say this is the array, and now I know that these are the elements that are appearing twice, and 3 is my answer. Anushka is asking how time complexity is big of n log n, because Anushka, we are sorting the array first, and because of that, the complexity is n log n. The sorting is the sorting takes n log n time, and then we also have to traverse the array. So it's actually n log n plus n. But since n log n is the dominant term, we don't consider this. We only consider the dominant term. That's why it's n log n. Yeah. So Ayushi and Pavan have the right idea that because each of these elements occurred twice, and we saw a property that A exclusive OR of A gives you a 0, and A exclusive OR of 0 gives you an A. So we can use that property some here, right? And what we can do is we can take XOR of all of these elements. If we take XOR of all of these elements, this one and one will evaluate to 0. This 2 and 2 will evaluate to 0, and we will have a 3 left over. Now 0 XOR 0 is again 0, and 3 XOR 0 is 3. So we get our answer back. So we get the unique element. And see, this solution works because XOR, and not just XOR, even and bitwise OR, all of these operations are communicative and associative, which means that whether you do A XOR B or you do B XOR A, it doesn't matter. It's going to give you the same result. This is called the associative property or communicative property, sorry. And its associative property is that if you have to take XOR of 3 elements, it doesn't matter if you take XOR of A and D first and then XOR the result with C, or if you take the XOR of B and C first and then XOR it with A. It doesn't matter. It's going to give you the same result. And because of these two properties, we can actually do this. We can take the XOR of all elements, and we can be sure that the order doesn't matter, and we will get the unique element no matter what. So did everyone understand that? Yeah, Lalit, we will be discussing that next. Okay, so Sumit is asking what will be the time complexity. Okay, Sumit. So all we are doing is traversing the array and taking the XOR of all of these elements one by one. So the time complexity will be linear or big O of n, where n is the size of the array. And the space complexity is going to be big O of 1 because we are not taking any extra space. Like the only extra space we are taking is the looping variables, but that is constant. That doesn't depend on n. So it's going to be a constant space. Ayushi is asking, what if repetition is not twice? Okay, so I'll give you a general case where this XORing all the elements would work. If the repeating elements are repeating an even number of times, it doesn't matter if it's two, it can be 2, 4, 6, 8, anything, but it has to be even. And the one number that is not repeating can actually repeat, but it has to repeat an odd number of times, right? So if you satisfy both of these conditions, that the repeating numbers are repeating even number of times, and the number that we want to find is not repeating, or if it's repeating odd number of times, then this XOR approach would work. Because if you take a XOR of the same element odd number of times, it's going to give you the number back itself. But if you take the XOR of the same number even number of times, it's going to evaluate to 0. Because all two twos will evaluate to 0, and all of those zeros then will finally give you another 0 back. But if it's an odd number of times, if it's a repeating odd number of times, then for every two number of twos, you will get a 0, and then there's going to be a 1 2 that is repeating. That is that is left out because the remainder is 1. So 1 2 will be left out, and that would give you back the same number that we had. Okay, so you got it, yeah. So okay, so let's. It's a similar question to this one, but there's a slight difference. Again, we have an array with numbers, and all of the numbers are repeating twice. But there is not one, but there are two numbers this time that only occur once. And we have to find those two numbers. So for example, if my array could be uh, something like this maybe. So you can see that 1 and 2 are repeating twice, and 3 and 5 are only occur once. So what we want are these two numbers, 3 and 5. So how can we? So see now, because the solutions that were not bit manipulation solutions, they were very general solutions. You can use those solutions again to to find to find the answer of this question. Again, you can make a hash map, and all of the elements will give you the frequency of XS2, but there will be two elements, let's say A and B, which will give you the frequency as 1. And again, you can find that okay, A and B are my numbers. Or you can do a sorting, and this you'll need to handle a couple of cases as well, because this time that watching the left and watching the right won't work, because if the two elements that are uh, that occur once come together, then this approach may fail. So you will need to have an extra check. And they work because they were general solutions, so they can accommodate all of these different variations in the questions. But we still want to use that bit manipulation operation that we learned before. We still want that our solution give us an big O of n time and a big O of 1 space. So can anyone think of a solution, or maybe maybe a hint, or maybe a start somewhere? How can we start with this question? If you could mention that in the chat. Okay, so Sumit is saying same XOR. Anyone else? Okay, so let's try out Sumit's idea. So again, we will take XOR of all elements. So 1 XOR 2 XOR 1 XOR 3 XOR 2 XOR 5. So again, the repeating elements, because they're repeating twice, so the repeating elements are going to evaluate to 0, and the non-repeating elements are going to evaluate to themselves. So finally, you are going to get this result. If the two numbers I had that were occurring only once were A and B, so XORing all the numbers will give you A and B. A XOR B. So now the question is basically if we can somehow separate these two numbers from this resultant, which is A XOR D. If we can get A out and B out, then we will have our answer. So how can we do that? So actually first, let's try this with this example. Let me just copy down the array first, 1 2 1 2 3 5. And let me use 3 bits for each number to represent them. So 1 would be 001. Actually, let's look at 3 and 5 only because we know that the repeating elements would collapse to 0. So 3 would become as 011 and 5 would become as 101, right? So this is the binary representation of 3 and this is the binary representation of 5. And the resultant that we would have gotten if we had XORed all these elements would have been 1 1 would give us 0, 1 0 would give us 1, and 1 0 would give us 1 again. So this number is 7 minus 1, 6. This number is 6. So if we evaluated this array, we evaluated the XOR of all the elements, we would have gotten a 6. So we have this. Or more specifically, if you were actually writing a program, this would be all 32 bits and all of these other bits would be 0. So see, if I know that this number, this 6 right here, is a XOR of two numbers, right? Only two unique numbers. Then I also know that if there is a 0 in any bit, I know that the bit at the same position, the bits at the two numbers A and B would be the same, would have been the same, right? That's why I got a 0 here. Either they both would have been ones or they both would have been zeros. That's why I got a 0 in the XOR resultant. And if similarly, if I see a 1, then I know that in A and B at this position, which is the first bit, the first position, either A was a 1, B was a 0, or A was a 0, B was a 1. B had a 1 in that position. So they were different. I don't know exactly which bit A had and which bit B had, but I do know for sure that they were different. That if one was 0, other was 1. So can we somehow use this to separate these two numbers? Can you think of a way now? Okay, Payal is not getting it. Okay, Payal, let me just explain it again. So you understood that when we XOR all the elements, we are going to get a 3 and a 5, right? We are going to get 3 XOR 5. For that example, the resultant by XORing all of the numbers, we are going to get 3 XOR 5. And we've then found out the value of 3 XOR 5 to check it in more detail. and the value of 3 in binary is 0, 1, 1, and the value of 5 in binary is 1, 0, 1. So 3 XOR 5 would be 1, 1, 0, and all the trailing zeros because they are 32 bits, assuming these are integers. So now this is the resultant of 6, the resultant of 3 XOR b, which is 6. Now if I look at this number and I look at each of the bits specifically, if I see a 0 here at the 0th position, this is the 0th position. If I see a 0 at the 0th position, I know that the two numbers 3 and 5 definitely have the same bits at the 0th position. They could both have been ones, or they both could have been zeros. Right? Did you understand that? That if there's a 0, because XOR only gives you a 0 when both of the bits are same. So I know if it's a 0, then both of the bits in those numbers would have been the same. Either both would have been 1 or both would have been 0. Okay, yeah. Okay, so you understand that. And if it's a 1, then I know that the bits at that position in both of these numbers was different. So if one number had a 0 in that position, the other number would have had a 1. Like there's no other possibility. Either the first number was 0, second was a 1, or either the first was a 1, second was a 0. They will both be different. That's all I know. I don't know the exact bits, but I do know that they're different. So now my question is, using this information that we know that these two bits are going to be different in these numbers, can we use this information somehow to separate the numbers from this combined XOR result that we have? We don't have 3s or 5. We don't know 3s or 5. We only have 6. We have taken examples, so we know 3s or 5. But when we get the result by XORing the numbers, we are only going to know 6. So how can we use this 6 to separate this 3 and 5? Okay, so Udit is suggesting something. So Udit is saying if we do x and minus x, where I'm assuming x is A XOR B, we will get a mask, and then take and with mask so that we can separate 3 and 5, then again apply XOR to two lists. Okay, Priyanshu is saying if 3 equal to XOR, then 5 equal to XOR minus 1. But Priyanshu, if 3 equal to XOR, like you're saying, then 5 can't be XOR minus 1, right? Because if you're saying XOR is 3, then this evaluates to 3 minus 1, 2, which is different than 5. Okay, so let me explain. Okay, so let me explain it. So let me just write down 6 again. If I could take every element, right? If I could take every element in the array and make two groups, group 1 and group 2, which are going to be mutually exclusive, right? These are mutually exclusive, there's no overlap. And in group 1, let's say I put all of the numbers which have a 1 in this position. If this is 0, this is first position, second. So it has a 0 in first position. I put all of those numbers in group 1. And then in group 2, I put all of the numbers that have a 1 in first position. Right? So what this would do is, in group 1, it's going to give me some elements. And in group 2, it's going to give me some elements again. Right? So let's say in group 1, let's see exactly which numbers are going to be in group 1 and which elements are going to be in group 2. So 1, 2, 1, 2, 3, 5 was my array. So 1 is going to be 0, 0, 1, 2 is 0, 1, 0, 3 is 0, 1, 1, and 5 is 0. So first place, there's a 0 in first place. So which elements have a 0 in first place? 2 and 3. So in group 1, both the 2s will come and the single 3 would come, right? And then in group 2, 1 in first position. Oh, so, actually I made a mistake, sorry. This one is 0 in first place. Let's say this is 1 in first place. And this one is 0 in first place, right? So in group 1, we will have the 2 2s and the 3. And in group 2, we have a 0 in first position. So all of the numbers which have a 0 in first position are going to be placed here. Aman is asking why first position? Well, Aman, because the first position is the one that has a 1 in it. We could have taken 2 as well. We could have taken any position that has a 1. But we are taking this first position because we saw a method of extracting the lowest set bit, right? We saw a method by which we can easily extract the lowest set bit. That's why we are taking the first position. But actually, this would work if you take any position that has a 1 in it. I could have taken 2, like I could have taken G1 as 1 in second position and G2 as 0 in second position. Basically, what I have to do is just make 2 groups that are mutually exclusive. So I could have used any bit that has a 1 in it. So is everything clear till now? Okay, so okay, everybody is replying yes. What is first place here? Sumit is asking what is first place here. Sumit, the first place is going to be that same I that we discussed back, right? When we were setting the ith bit and unsetting the ith bit. So I is the position. So in this number, first is this position, the position of this 1. That is also 1. So by first place, I mean the position of the bit, which is 1 in this case. That's the first position. So I'm calling it as first position. This is the 0th position. Yes, Lalit, we can do this to all 1, like all of the ones. We don't have to stick to this first one. We could have taken any other one. Let's say if the XOR resultant were something like this, then we could have taken this position. 3, 4, fifth position. We could have taken the fifth position. So we could have made G1 as 1 in fifth position and 0 in fifth position. We could have done that, and that would still work. The only reason we are taking the lowest set bits position is because we can easily extract that by doing x and minus x as we saw earlier. Yes, Ayushi, before doing this, we need to check that where I is present. But if you were present during that section, we saw that we can actually do that by doing x and negative x. We don't have to explicitly run a loop and get that position. We can just make a mask that has a 1 at that position and zeros everywhere else by doing that x and minus x thing that we learned earlier. Yes, yes, Udit, you are correct. Now that we have a mask which has a 1 at the lowest set bit of the XOR resultant that we have, right? It's going to be, it was 6. Yeah, it was 110. So my mask is going to be something like this, right? And now all I have to do, now that I have this mask, all I have to do is now I will again iterate through all of the elements of the array. And now I will identify the bit which has a 1 in it. So in this case, I equal to 1. So for every bit, for every number, I'm going to identify the ith bit, where I is equal to 1 in this case. And if it's 0, if that bit is 0 for a number, I'm going to take their XOR separately. And if it's a 1, I'm going to take their XOR separately, right? So we use the and negative x and minus x concept, and we also use the identifying bits concept as well in this question. Somebody was asking, way back in that section, why identifying is important. So here it is important. See, here we have to identify like which bits are 1, which bits are 0, which numbers have that position as 1 or 0. Cheryl, I will come to the code, like how do we code this? I'll come to that. Okay. So now if everybody has understood this, now we can get to the code. If everybody has no doubts, you can just say no doubts. And then we'll go to the code. Okay, no doubts by Apple. No doubts. Yeah, Payal, we'll see that when we start the code. So actually, nobody has a doubt. So let's move on to the code, right? Okay. So I'm trying to write a pseudo code, which hopefully is language independent. So for I equal to 0 and let's say the size of the array is 1, n. So I'm going to run a loop. And first I'm just going to find the XOR of all elements. So initially XOR is equal to 0 and my array's name is ARR. So first I'm going to find the XOR of all elements. Okay, that's done. Then I'm going to find the mask. The mask which has a 1 in the lowest set bit and 0 everywhere else. So that can be found out by XOR and negative XOR. Right? So this is going to give me that mask. Now, and see, in this entire question, I'm not concerned with the position of that set bit because that is already being considered when we do this, XOR and negative XOR. So we won't have to write the position in the code itself because that is being handled automatically by this expression. Okay, so for now, we'll again run a loop. And this time, we are going to identify that bit. For each number, we are first going to identify what the bit in that position was. So that can be done by if mask, if ARR of I and so how do we identify the number? How do we identify a bit? We do an AND with the mask. So I don't have to left shift anything because the mask itself has the one left shift the position. Let me just write this piece of code on the next page actually, because this is the core logic of the program, right? Okay, so if my element I hand it with a mask, if it is 0, then that means that position, the lowest set bit position for ARRI was actually 0. So in that case, I can do XOR1 equal to XOR1 XOR of ARRI. And else, if that bit was not 0, I can take a separate XOR for these elements. Right? And finally, XOR1 and XOR2, and like not the bit operator and, XOR1 and XOR2 would be the two numbers that we wanted. Because this piece of this if condition is actually XORing all the G1 elements, and this the else condition is XORing all the G2 elements. And then we can print XOR1 and XOR2 or return them, or depending on the question. So please dry run the code. Sure. So let's take that same example that we had before. So let's first write the binary numbers of all these numbers. Let's represent them in binary first. Okay. Now the code which was the variable which was named ZOR in my code, that variable is going to store the value of 6 for this array, right? And for 6, if we have a 6 here, which is 110, and all of these zeros leading zeros. So my mask, the variable mask in this for this data, this input would be these trailing zeros, then a 0, then a 10. Okay. Now for each element in the array, we are going to identify which bit this position has in these numbers. So first we do 1 and this mask, which is going to be 0, 1, 0. I'm just using 3 bits for now because all of the other bits are zeros. So 1 and mask would be 1 and mask this. This is 0, this is 0, this is 0. So 1 and mask gives me a 0. So this means that 1 is going to be XORed with XOR 1. So XOR 1 was initially 0, and XOR 1 is now XORed with 1 to give me XOR 1 equal to 1. Okay. Then next we have 2. Again, the mask is the same, and we XOR it with 2. We get a 0. Wait, there's some error here. Yeah, okay. Sorry. Okay, I found the mistake. This is 1 because we are XORing it. Wait, no. Okay, sure. Actually, you know what? Let me do that again because there was some confusion. Sorry, I apologize. Okay. Yeah, so XOR would be 5. Would be 3 XOR 5, which is 6. Okay. Now for each element, first we will take the binaries, which is this. Okay. Now for each element, we are going to identify the bit that the set position of this number has. So this is my mask, and my first number is going to be 0, 0, 1. And if I add these two, I'm going to get 1, 0, 0. So I got a non-zero value, which means that this bit was set. So I can put it in a separate group. Let's say I put it in the XOR 1 group, right? So XOR 1 is initially 0, and XOR 1 would be XOR 1 XORed with ARR of 0. Okay, and XOR 2 is left unchanged, still 0. Then for the next element, I have my number as 0, 1, 0, and the mask is 0, 1, 1. Again, the mask is going to be the same. Again, I do an AND. This one is 0, this one is a 1, and this one is a 0. Oh, actually, I wrote it correctly the first time. I don't know what's happening. Okay, I'm sorry. The mask is 0, 1, 0, and the XOR resultant would be 0. So XOR 1 is 0, and XOR 1 would be XOR 1, and XOR 1 with ARR of 0, which is 1. Okay, for the next element, the mask is 0, 1, 1, and the element in binary is 0, 1, 0. We do an AND, and we get 0, 1, 0, which is a non-zero value, right? So we know that the lowest set bit of this number is set. So we will put this in the other group, XOR 2 group. So we will update XOR 2 as XOR 2 XOR ARR of 1. So XOR 1 becomes 1 and XOR 2 becomes 2. Again, we get a 1. So 0, 0, 1, and we XOR it with the mask. Again, we get a 0. And if we get a 0, then that means it will be XORed with the XOR 1 group. So again, I do 1 XOR 1, which is 1 XOR 1 is 0. So XOR 1 becomes 0. Then again, I do it with 2 in the next iteration. And the result is going to be 0, 1, 0, which is non-zero. Then it will go to the XOR 2 group, which is 2 XOR 2, and XOR 2 will also become 0. Okay, so just 2 numbers are left, so let me just complete it. So 3 is 0, 1, 1, and the mask is also, yeah, the mask is the same as before. So again, we do a XOR, we do an AND, sorry. We do an AND, and this will go into the XOR 1 group. So 0 XOR 3. And 5, we know that 1, 0, 1 and 0, 1, 1. We do an AND, okay. 3 would actually, sorry, 3 would give a 0, and 5 would give a 1. So 3 would go into the XOR 1 group to make XOR 1 equal to 3, and 5 would go into the XOR 2 group to make it as 5. So XOR 1 equal to 3 and XOR 2 equal to 5 finally. Okay. Okay, so did everyone understand that? Okay, so Priyanshu is saying yes. Aman is saying yes, okay. Okay, so let's move to the final question of this webinar. And it's actually it's a good one. Yeah, so can you see this question? Can you see this screen? Yeah, Priyanshu. So basically we did A XOR D, and the entire question was to separate A and B by using the any set bit, because we know if there's a set bit, then the 2 bits would be different. Can you see this winning lottery ticket page? Screen is visible, okay. Actually, I think you may not be seeing this screen. Wait a minute. Yeah, question is not visible, okay. Okay, guys, I'm just fixing it. Just give me a moment. Okay, now can you see it? Okay, yes, okay. Okay, so let's take a look at this question. The Super Bowl lottery is about to commence, and there are several lottery tickets being sold, and each ticket is identified with a ticket ID. In one of the many winning scenarios in the Super Bowl lottery, a winning pair of tickets is concatenation of the 2 ticket IDs in the pair in any order contains each digit from 0 to 9 at least once. Okay. For example, so they've given an example, if there are two distinct tickets with these ticket IDs, then this is a winning pair because both of these numbers have the digits 0 to 9, right? So here's a 0, here's a 1, 2, 3, 4, 5, and then 6, 7, 8, 9 are together there. Okay. And there's a note that the ticket IDs can be concatenated in any order. So it doesn't matter which order they are in, concatenated. The smaller one could have gotten first. And the digits in the ticket ID can also occur in any order. Okay. So they don't have to occur in 0 to 9 order or 9 to 0. They can occur in any order. Okay. So our task is to find the number of winning pairs of distinct tickets such that concatenation of their ticket IDs is in any order makes for a winning scenario. Okay. So basically what it's saying is you have a list of tickets, right? And you can pick any two tickets and concatenate them. And that pair of tickets is going to be a winning pair of tickets if that concatenation that you just made has all of the digits starting from 0 to 9. And it only has to occur once, if I'm correct. Yeah. Yes, contains each digit from 0 to 9 at least once. So if all the digits occur in that concatenation at least once, then that is a winning ticket. So the order of concatenation doesn't matter, and the order of the digits also doesn't matter. So a brute force solution that comes to my mind is we can just check every pair, right? We can check every pair, and for each pair we are going to concatenate it, or not even concatenate. We are going to put each of these digits in a set, right? And after I have made that set, for one pair, I've made a set like that. If that set size is equal to 10, then I know that the pair that I just checked is a winning pair. Why? Because you know that there can only be 0 to 9 digits. Like there are 10 digits in total. And if concatenation has all of the digits, and I put all of the digits of that concatenation into a set, its maximum size could be 10. The set size could be at max 10. If it's 10, I know that all of the digits are present. If it's less than 10, then some digit was missing. Like we don't have to worry about which digit was missing. We just have to report that whether it's a winning ticket or not. So all of the digits are present or not. So the complexity of that solution where we have to check every pair. And the way we check it is that we take this ticket, the first ticket, and we concatenate it with every ticket that comes after it. And then we take the second ticket and we concatenate it every ticket after it. So the time complexity would be n square, right? N square. And if you are considering the concatenation process is also taking time because you can see that the length of tickets, there's also a constraint given for the length of tickets, and it can be 1 from 1 to 10 to the power 6. So there can be at max 7 digits in a ticket as well. So if you're counting those, and then the complexity is actually going to be n square times k, where k is the number of digits per number, the average number of digits for every number, k. So then we have that k factor as well. But otherwise, if you're treating it as a constant operation, then it's going to be at least n square, which is still bad, right? So let's see exactly why we are getting this extra time. Like why there must be something that we are doing wrong, or we are doing something that is not required. So first, all we need to find is that every pair should contain these digits 0 to 9 at least once. We don't care about the order. We don't care about whether that digit occurs multiple times. Like if 0 occurs 3 times, we don't care. It only has to occur once to make to be considered for a winning lottery ticket. So is there a way where we can, for each number, we can make, we can represent these numbers in a way that only captures this information? And that information is that whether a digit occurs in that number or not. because that's all we need. We don't care about the order. We don't care about how many times it's coming. So is there a way we can represent these numbers in that way that we only get the essential information out, basically? Okay, so Priyanshu is saying we need to loop. Yes. Winning pair equal to pair into size of pair. Order is order minus one every time it occurs. Use counter, I think. Okay. Okay, Priyanshu. So how would you use that counter? Like, how would you use a counter? How would you represent this number using a counter? And since this is a bit manipulation webinar, so there has to be, there has to be something to do with bits. So think of that in that way. Vishwajit, this is the final questions. We are just wrapping up after this. And I will send the links that I mentioned before, the bit manipulations. I'll send that link after the webinar. I'll post it as a comment on the video. So this is just the last question. So please bear with me. Okay. I think nobody's replying. So, okay. So let me just, let me give you one way to represent these numbers, right? So let's say my ticket is something, it's very big, something like this, right? I know the constraints on the ticket are 10 to the power 6, but let's say the constraints were not this, they could go anywhere. So let's say I have a ticket like this, right? So it has a 0, it has a 1, 2, 3, 4, 5, 6, 7. It doesn't have an 8, right? So what I can do is I can make 10 bits, a collection of 10 bits. 7, 8, 9, 10 bits. And every position in this collection of bits that I have, every position is 1 if that number is present in this big number, and if it's 0 if it's not present. For example, the 0th position is going to be 1 because 0 is present in this number, right? Similarly, 1 is present in this number, so 1's first position will have a 1. Second position will be a 1 because there's a 2 present. Third position will be a 1 because there's a 3 present. Similarly, 4 would be 1. 5 would also be 1. 6 would be 1. 7 would be 1. 8 would be a 0 because 8 is not present anywhere in this number. So 8 would be 0. And the 9th position is going to have a 1 because we have a 9. So did everyone understand that? Yes, Aditi, the video will be available later. Okay. So how exactly does this help me? First of all, it condensed this huge number into just 10 bits, right? All I need are 10 bits to store this number because this number only stores the information that I need. Plus, it also, what it does, it also stores other numbers that have these same numbers present in it. Let's say there's a number like this, right? And let's say there's a number like this. So all of these numbers are not considered to be different in this system that we are using. All of these 3 numbers are actually represented in the same manner, which is these bits. So not only does it condense very large numbers into 10 bits, but it also we can use the same representation for multiple numbers. So this actually reduces the number of numbers that we are working with considerably, right? Okay, so this concept is very important. So are there any doubts till now? Okay, no doubts by Priyanshu. Please repeat the concept once more. Okay, let me just explain it again. See, all I really wanted from these big numbers was whether a particular digit was present or not. I didn't want to know the frequency. I didn't need to know the order. All I needed to know was, yes, this digit is present, this digit is not present. For each number, I had to do this. So I just came up with a system that, that consisted of 10 bits. And for each bit, the position represents whether whether that digit is present in this big number or not. So if the ith position is 1, I know that whatever number this is representing, that number has at least 1 4. Similarly, if there's a 6 and it is 1, so I know whatever that number is, however big it is, it at least has 1 6. Now I see 8 is 0. Now I know that 8 is nowhere to be found in that number. That 8 digit is not present. So I condense the information of this big number into a smaller number, into just 10 bits. And the second advantage that I get for using this system is that this same representation, we could have gotten the same representation for multiple numbers. So for example, this number and this number and this number, the bit, uh, the bit representation of these numbers, of all these three numbers, is this only. It's the same, right? So Aman, any doubts? Okay, so I think everybody got it. So, okay, all clear. Okay. So now, for every number, we are going to make a representation like this, right? And so we will have a collection of some representations. Let's say I'm only using 4 bits for now. Let's say the winning ticket is only 1 0 1 2 3, right? Let's use 4 bits for now, so it's a little bit easier to explain. So I could have multiple representations like this. Maybe there's one like this, maybe one like this. Right? So there could be multiple representations. And every representation is going to have a frequency attached to it as well. Let's say this. Now, the frequency tells me how many numbers, how many tickets are present in that collection that have this representation, this bit representation. So that means there are three numbers. This means that there are three numbers that have at least 1 0, at least 1 1, or at least 1 3, and no 2s. Similarly, this tells me that there are 4 numbers that have all the digits in them. This one tells me that there are 3 numbers that only have a 0, and so on. So we condensed our data, and now I want to concatenate 2 numbers to get another number, and I want to check whether that number that I've got has all the digits or not. Now, the representation of a number that has all the digits is all ones, right? If a number has a representation like this, it means that it has all the digits at least once. And this would be the bit representation of a concatenated ticket, of a concatenated winning ticket, right? Now, if we were dealing with just numbers, we had to physically concatenate them and then count whether all the digits are present or not. But if you're working with bits, what is an alternative of concatenation when it comes to bits? Which bit operator does the same thing uh, as counting all of the numbers, all of the digits in the concatenation? Like which operation I can use to find out whether two numbers, when I concatenate them, they are going to have all of the digits. Yes, Sargun, this video will be available later. Vedika will send the link after this webinar is over. Like you can check the YouTube video for this, and there's going to be a comment which will have the links for the codes. Okay, Apol is saying or, and any other guesses? Okay, Vishwadeep is also saying or. Okay. Okay, so it's or. Why? Because let's say I have a number that has the bit representation of this. And let's say I have another number which has the bit representation, let's say 1001. If I concatenated these two numbers, I'm going to get a number that has at least 1 0. I'm going to get a number that has at least 1 1. I'm going to get a number that has no zeros, that has no twos. And I'm going to get a number that has at least 1 3, at least 1 3. So by ORing these two numbers, I can actually get the bit representation of the concatenated ticket, right? So now that I know that, now all I have to do is I have to run a for loop again. I still have to check every pair, right? But now I don't have to check every pair of from the ticket list. Now I have to check every pair from this bit representation list. And the bit representation, the maximum number of bit representations that I can have is 2 raised to the power 10, because there were 10 bits, right? So there are going to be 10 bits. And since there are 10 bits, the total number of representations could be 2 raised to the power 10. Every place can have a 0 or a 1 or 1. So 2 choices for every bit. That gives me total possibilities as 2 raised to the power 10. We'll see the Priyanshu will see the time complexity after we solve this question. We'll explain the see the time complexity and space complexity as well. Okay. Okay. So any doubts till this point? Okay, no doubts by Priyanshu. Rahul, we will look at the analysis after the question is done. Apol is saying no. Okay. Okay, so now that we know that we can, there are 2 raised to the power 10 possibilities, and that we can OR 2 tickets to get the combined ticket. All we have to do now is apply a for loop for each representation. Now, each representation starts with 10 zeros and it goes till 10 ones, right? So this is the minimum value of a representation, and this is a maximum value of your representation. And maximum value is going to be 2 raised to the power 10 minus 1, right? So it's going to be 1023. So for I equal to 0, I less than less than equal to 1023 and plus plus I. And let's say for j is equal to I plus 1 and j less than equal to again 1023 and plus plus j. First, we are going to find if I or j is equal to 1023, right? If it is, then we know that I and j combine to form a winning ticket. So the number of pairs possible is going to be the number of tickets that have the representation as I multiplied by uh, the number of tickets that have the representation as j. So the counter is going to be frequency of I times frequency of j, right? But there's one special case that you need to handle. It's that if a ticket by itself is all ones, then it can combine with any other ticket, right? So in that case, we can't find the number of pairs by doing frequency times I into frequency times j. If both I and j are equal, right? They're both equal and they give their OR as 1023. We know that I and j are both are equal to all ones. So in that case, we are going to find IC2 instead, which is the number of count of all the pairs that you can pick out of I numbers, a frequency of I, rather not I, frequency of IC2. So if I and j are different, you're just going to do multiply their frequencies. And if I and j are both equal, then you can do frequency of IC2. And finally, you can add all of these. Instead of doing counter equal to this, you can do counter plus equal to this. And similarly, counter plus equal to frequency of IC2. And the final answer, counter, is going to give you the number of winning tickets. Okay, Priyanshu is saying, I could do one, yeah, Priyanshu, you are sending the code for making these bit representations. First, we are discussing if we have the bit representations, how can we calculate the number of. Okay, so Rajat is asking why I or j equal to. So Rajat, it's I bitwise or j. Okay, it's not double. It's not this one. It's this single pin, right? And we do this because see, our bit representations had 10 bits, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so our bit representations had 10 digits, and we know a winning ticket is formed when it contains all of the digits. And if a number contains all of the digits, then its bit representation is going to be all ones. And all ones in this system, if we are writing 10 times 1 in the binary system, in decimal, it's going to convert to 1023, which is 2 raised to the power 10 minus 1. They're 10 bits. If they're all ones, so this is the number that it represents. That's why we are doing 1023. So is that clear now, Rajat? Okay, got it. Okay. So now it's getting a bit late, so we'll quickly discuss how can we make these bit representations, right? So now we will use what Priyanshu said earlier. For each ticket, uh, and even for each ticket and for each ticket character, we are first going to make a mask. Mask is just a bit representation. I'm calling it as mask. So for each ticket character, what I can do is I can do mask and or it with one left shift that character typecasted into an integer. So if it's the 0 character, I have to take 0, the integer 0. If it's 1 character, then I have to take the integer 1. And this can be found easily by doing this. character minus character 0. So this subtracts the ASCII codes of the character and the ASCII code of 0 and gives you the integer value, right? So this can be done. This thing can be done by this. Okay. Okay, so for each ticket character, you're going to OR the mask with this one left shift with the integer representation of the character. And then to store the frequency of this mask, of this bit representation, you can make a hash map, right? Or you can make a 1024 sized array, whatever you feel like. Let's call it frequency. So frequency of mask, you can increase it by 1. Okay. And when you have traversed through all of the tickets and all of the characters, you're going to get the map or the array with all of the frequencies stored on it. And when you have this frequency, all of the frequencies, then you can do that loop that we had earlier from j equal to 0 to 1023. And then if I or j is all ones, which is 1023, then you have to do another check. If I and j are not, if they are different, then you do frequency of I into frequency of j. But if I and j are equal, then that means you have to do frequency of IC2. So chronologically speaking, this code will come first. First, you have to find the frequencies, and then you have to do the counting. Okay. Okay, Rajat. Okay, Infinity Magnum. Thank you. Frequency is the array of size. Yes, frequency is the array of size 1024, or it could be even a hash map if you like. But I prefer an array because even though theoretically speaking, hash maps have a big O of 1 frequency for adding elements or updating elements, it can be different. But for arrays, you can be sure it's big O of 1. So I prefer using an array rather than a hash map. If I know the elements themselves and I know the size of the unique elements that I'm going to get. So yes, in my case, frequency is going to be the array. Yes, Ayushi, the codes will be present. They will be posted as links in the comment section of this video only. And I will also give you that other bit manipulations that I was talking about. So we are just coming to that. So this question is basically done. So if anyone has any doubts, you can ask them, or we can conclude the session now. Okay, Priyanshu is saying no doubts. Apul, this was an interview question. And see, mostly interview questions are going to be like this. They are not going to say to you that you set an IR bit for me or unset an IR bit for me. These questions, the questions that will be asked in interviews, are going to be ones that have all these manipulations that we did, these small manipulations as intermediate steps. See, so to do that, all those repeating elements and 2 of them are not repeating, we had to use those basic manipulations in them, right, to find the to make the mask of the lowest head bit position. We have to make a mask for that, and to identify those bits, we have to make use of those operations. So if you have those operations, all you need to do now is all you have to do now is make use of those manipulations to construct the final answer, like we did in this last problem. And I was saving this for the last because I wanted to get the basic questions out of the way first, because this would have been very difficult to understand for beginners if they were not aware of the basic manipulations that we learned earlier. But this is actually an interview question. This one, the winning lottery ticket one. Yeah. So finally, let's discuss the time complexity and space complexity of this code. So see, time complexity is, first we are traversing to make the bit masks, we are traversing all of the elements, right? We're traversing all of the tickets and we're traversing all of the characters as well. So basically you can say we are traversing all of the elements. And if there are n numbers, let's say n tickets, if there are n tickets and every ticket has on average k digits, then essentially your time complexity would be big O of n times k plus, in the second step, what we are doing is we are running this double loop from 0 to I is equal to 1023. Now 1023 is a big value, but it is smaller compared to 10 raised to the power 6. So if you want, we can consider it to be big O of 1. But if you don't want to consider it as a constant, if you want to represent it as as some variable, then 10 we got the 10 bits. We got the 10 bits because the digits were from 0 to 9, right? So that's why we use this system of 10 bits only. And that's why we got the 2 raised to the power 10 factor. Now, suppose if the question were something else, the question were like instead of numbers, the tickets were actually words, and you had to concatenate 2 words to make a ticket that had all the alphabets once. Then you would have used a 26-bit system, and in that case, your the loop that you would have been running would have been 2 raised to the power 26. So 2 to the 26 is a considerably, it's a very large number compared to 2 to the power 10. So in that case, you might include it as a variable rather than considering it as big O of 1. But in this case, 1024 is not a big value, right? So we can consider the second loop as a big O of 1 operation. So the overall complexity is n times k. And the space complexity is, again, it's going to be, we are making a fixed size array of 1024. That's the only space we are using. So the space complexity is also big O of 1. If this were a lot bigger, maybe like in the alphabet case, then you could have mentioned it as a variable rather than big O of 1. Right? Yeah. Okay. Yeah, Infinity, I agree with you. Yep. It's time for mercy. Just a final closing thoughts I want to give. It will take 2 minutes max. So this is the wait. Let me just share my screen again because there it is. Yeah. So this Wikipedia page, bit manipulation instruction set, has all of those manipulations that I was talking about. As you can see, extracting the lowest set bit, set isolated bit is x and negative x. Get mask up to lowest set bit is x, XOR x minus 1. Reset lowest set bit is this. And then there are other ones here, like at the bottom. So see, my suggestion to you would be, rather than reading this description and mugging this equivalency expression, what you can do is just hide this column, this equivalency expression, and try to figure out the expression yourself first. See, because that is going to give you the necessary practice, that how bit manipulation is actually working, how you can use these operators to change bits and modify them to suit your situation or to get the output that you want. So that is the way I would suggest that you go through with this, rather than just simply mugging it up, right? And as far as questions go, like we all have platforms to go to. Like I can suggest you a couple. Our Coding Ninjas practice session has a lot of bit manipulation questions in them. Then if you complete all of those questions, you can go to Deep Code to maybe filter those questions by difficulty or maybe by companies, whatever you feel like however you want to do that. So, but before you try out actual questions like this winning lottery ticket question, I would first suggest that you do this thing first. Like, try to figure out these expressions by yourself, and then move on to those other questions like this winning lottery ticket and all. Yeah, yeah, I will provide this link. Actually, yeah, I will just provide this link. Don't worry about it. Let me just open up that live session and here. Uh, yeah, there you go. And here's the winning lottery ticket question. If you want to code it out, even though we have seen the explanation, still, if you want to write the code for it, and here's the link to the HackerRank problem. And I will be posting the links to the codes of all of the things that we have discussed shortly. Okay, so have some patience. By tomorrow morning at max, it will be done. So, okay, guys. So let's conclude the webinar. And I know it got not a bit extended, not extended by a lot, but still I hope you learned something new. And if you knew something already, I hope I was able to give a better explanation, a clearer explanation, right? Okay. Okay, guys, if you have any other doubts, relating to these questions, bit manipulation or any other things, then you can just hit me up on LinkedIn. I'm sure. I mean, the ad for this, the post for this had my LinkedIn profile as well, so you can contact me there anytime. Okay, and it's 11:12, so I think I should end the webinar now. Thank you for your patience. During the start, I had some problems. Thank you for seeing this webinar till the end. Rajat, LinkedIn ID. If you open up LinkedIn and you go to the Coding Ninjas page in LinkedIn, you'll see that they have posted a post which has my LinkedIn linked there already. So you can just click on that and visit my page. Okay, thank you everyone. So let's not take more of your time and let's end this stream. Okay, thank you and good night. Right.